It is 3 in the morning at the Institute for Quantum Optics in Vienna. A single electron has just passed through a pair of slits 10 nanometers apart. The dot on the phosphor screen behind it lands at one precise location, and after 100,000 more electrons fired one at a time, the screen shows the unmistakable interference pattern of a wave, even though each electron arrived as a single particle. Tonight, we cover quantum mechanics. Joining me are a theoretical physicist and an experimentalist.
Quantum mechanics is the fundamental theory of physics at the smallest scales. This theory is built around four mathematical postulates. 1. The state of any physical system is fully described by a vector in a complex Hilbert space called the wave function. 2. Observable quantities correspond to Hermitian operators on that space. 3. Measurement outcomes are eigenvalues of those operators, with probability equal to the squared modulus of the wave function projection. 4. Between measurements, the wave function evolves deterministically according to the Schrödinger equation.
The Schrödinger equation was written down in 1926 by an Austrian physicist. It relates the time derivative of the wave function to the energy operator acting on the wave function. The wave function itself has no direct physical meaning. The Born rule, proposed by a German physicist that same year, states that the probability of finding a particle at any point in space is equal to the absolute square of the wave function value at that point. The wave function is a probability amplitude. Probability emerges only from its absolute square.
Heisenberg's uncertainty principle is built directly into the operator structure. The position operator and the momentum operator do not commute. Their order of application matters. The commutator equals I times h bar. Mathematically, this forces the product of the uncertainty in position and the uncertainty in momentum to be greater than or equal to h bar divided by 2. This is not a measurement limitation. The electron does not possess simultaneously a definite position and a definite momentum. The uncertainty is a property of the physical state itself.
Wave-particle duality is the most famous experimental signature. The double-slit experiment, performed with single electrons fired one at a time, shows the electrons land at specific points on the detector. Each electron is a particle. But the accumulated pattern after enough electrons is the classical wave interference pattern of bright and dark fringes. The electron passes through both slits simultaneously as a probability amplitude, then arrives as a single dot. Observe which slit it took, and the interference vanishes. The observer participates in the experiment.
Quantum entanglement is the strangest prediction of the theory. Two particles can be prepared so their wave functions are jointly correlated in a non-classical way. The Einstein-Podolsky-Rosen paper in 1935 showed it implies non-local correlations called spooky action at a distance. Bell's theorem in 1964 turned the question into a measurable inequality. Experimental tests in 1982, 98, and 2015 showed Bell's inequality is violated by quantum mechanics. The 2022 Nobel Prize in Physics confirmed it definitively.
The measurement problem remains the central puzzle. Before measurement, the wave function is a superposition of many possible outcomes, evolving smoothly via the Schrödinger equation. After measurement, only one outcome is observed. The wave function appears to collapse instantaneously to a single eigenstate. What counts as a measurement is not defined inside the formalism. The decoherence program of the 1970s and 80s showed how interaction with an environment effectively suppresses interference between branches, but the collapse remains philosophically contested.
At least four mainstream interpretations of the theory exist. The Copenhagen interpretation from 1927 treats the wave function as encoding observer relative knowledge and accepts collapse as primitive. The many worlds interpretation from 1957 argues every measurement branches the universe, collapse is illusion. The pilot wave or Bohmian interpretation from 1952 posits hidden particle trajectories guided by the wave function. Cubism treats the wave function as personal belief. No experiment to date distinguishes between them.
3 takeaways. First, quantum mechanics is the theory of the smallest scales. 4 postulates. Schrödinger equation evolves the wave function. Born rule extracts probabilities. Second, Heisenberg uncertainty is a property of the state, not the measurement. Wave-particle duality, entanglement, and Bell inequality violation are all confirmed experimentally, the 2022 Nobel Prize. Third, the measurement problem remains unresolved. 4 mainstream interpretations exist. Quantum computing, cryptography, and the entire modern semiconductor industry rest on the theory. Thank you, theorist. Thank you, experimentalist.